You ever get that feeling that, like, some people just have a secret map to how the world really works?
Mm.
Not some dusty old conspiracy, but, you know, a fundamental way of seeing things. Unlocking secrets hidden right there in plain sight.
It's a fascinating thought, isn't it? That sense that there's maybe a deeper logic under all the chaos we see.
Yeah.
And, in a way, there is a kind of secret society. The people who get the power of looking at the world through a certain lens.
Exactly. And that is precisely what we're going to dive deep into today. You sent over this really thought-provoking bunch of articles and notes, all circling around this core idea, understanding the world through basically 10 fundamental equations.
Right.
Think of it as like your express ticket to feeling seriously clued in.
Well, if you step back, what we're really talking about is a powerful way to kind of cut through the noise.
Yeah, the noise of our, complex world.
Exactly. It's about spotting the underlying patterns, the principles driving so much of what we see.
Our guide for this whole thing is David Sumpter's book, The 10 Equations That Rule the World. And he kicks it off with this great little story.
Oh, the Da Vinci Code one?
Yeah, about Sophie Neveu finding that mathematical code. It just, bam, grabs you with this idea that there's this hidden math structure underneath everything.
And what's so good about starting there is it shows these aren't just, abstract math things locked in textbooks.
Right.
They're actual tools.
Yeah.
Tools for deciphering the world around us in real ways.
And Sumpter, he lays out this central concept pretty quick. To really grasp how things work through this lens, you guys start thinking in terms of data, model, and nonsense.
It's item model nonsense, yeah.
And he makes this strong case that this whole approach is getting incredibly powerful now because we're just swimming in data.
Oh, totally. Just drowning in it.
But think about it. The stock market's constantly flowing. All the info from Facebook, Instagram.
Government data, sports stats, it's everywhere. And this explosion of data, it gives us this huge opportunity, right?
Yeah.
But also a big challenge.
Okay, how so?
Well, the opportunity is we can build these incredibly sophisticated models to analyze it all. But the challenge is figuring out what actually matters.
Right.
Separating the useful stuff from just noise.
So our mission today, basically, is to explore how these 10 equations, this data model nonsense framework, can give us some honestly surprising views on all sorts of things that seem unrelated.
Yeah, those aha moments.
Exactly. The ones that can genuinely shift how you understand stuff.
And maybe for you, the listener, it's worth thinking. How often do you look at information and it just feels jumbled, confusing?
Right.
Our goal here is to show how applying this kind of mathematical thinking can bring some clarity, reveal connections you might not have spotted otherwise.
Okay, so let's start unpacking this. Let's look at how these mathematical models are making waves in some pretty unexpected areas, like sports betting.
Yeah, that's a great example.
You used to think it was all about knowing the teams, the players, maybe getting an inside tip, right?
Traditional knowledge. Gut feeling.
But Sumpter tells this story of Marius and Jan, who were apparently making serious cash using math, without even watching most of the games.
And what's really interesting there is the shift, right? Away from that gut feeling stuff to a purely objective data-first approach.
Totally.
Marius and Jan, they built this automated system. Its job was to find what they called soft bookmakers.
Soft bookmakers, meaning?
Basically, betting sites offering odds that didn't really match up with the true statistical probability of something happening.
Okay. So they were looking for mistakes, essentially.
Pretty much. Their whole strategy was finding those little discrepancies and, well, exploiting them.
Right. Looking for value where most people wouldn't, like betting on a draw, maybe, or really strong favorite, even if the odds looked low.
Exactly. It's not about that thrill of a long shot. Sumpter emphasizes it needs patience, focusing on the probabilities.
Yeah.
And this brings up a really key idea, having a genuine edge.
An edge, right?
It's not luck. It's not intuition. It's finding situations where your model says the chance of something happening is different from what the betting odds imply.
Sumpter even mentions this contact, James, who worked in sports trading. And James apparently said, if you really have a mathematical edge, the only thing stopping you making money faster is just how quickly you can physically place the bets.
Wow. Yeah, that's a different world from standard investing, isn't it? Typical returns.
Totally different.
It's all about consistently exploiting these tiny advantages but over loads and loads of events.
That's where the power of the modeling really shows up, finding and grabbing those little statistical edges again and again, systematically.
Yeah, their model also got into this thing called long shot bias.
Right, the idea that casual bettors tend to overestimate the chances of unlikely things happening.
Yeah, but their specific equation with those alpha and beta values he mentions.
1.16 and 1.25. Yeah, those. It suggested something maybe more subtle, that in games without a massive favorite, the bookies might actually undervalue the underdogs sometimes.
So backing the underdog could actually be the smart bet in certain cases.
Potentially, yeah. Which goes against the usual thinking.
It's a fantastic example of how a model can uncover insights that, kind of defy common wisdom.
He uses that Colombia versus Japan football match example.
Oh, yeah, where their model picked Japan as the better value bet, even though Colombia was the favorite, and Japan won.
Right. Really brings it home. And this kind of data-driven modeling, it's not just sports betting, is it? It's showing up everywhere.
Absolutely. All sorts of fields.
And one of the key tools behind this, as Sumpter explains, is something called logistic regression.
Logistic regression sounds a bit technical, maybe.
It does, but it's become incredibly powerful.
And it has an interesting history, actually. It wasn't invented for this stuff.
Oh,
No, it was developed back in the 50s by a statistician, David Cox, for analyzing, medical and psychological data initially.
Huh. So, figuring out factors linked to health outcomes.
Exactly.
Yeah.
Very different from how it's used now.
Which is where?
Oh, all over. Facebook uses it for ads, Spotify for music recommendations, self-driving cars use it to spot pedestrians.
Wow. Oh,
And
yeah.
get this. William Benter. This guy, obsessed with finding mathematical certainty in horse racing,
Yeah.
apparently used logistic regression to make, $1 billion.
$1 billion from horse racing using logistic regression.
That's the story. He approached it like a pure statistics problem, wrote these detailed reports, apparently, showing his winnings were down to math, not luck.
That's incredible.
And the funny part, Sir David Cox, the guy who invented logistic regression,
Yeah.
hadn't even heard about Benter using it to make a fortune gambling until Sumpter told him.
No way. That just shows how these tools, develop, for one thing, can just explode in totally different areas, unexpectedly.
It really highlights the versatility, the power of these mathematical frameworks. Logistic regression started in medicine, now fundamental across so many fields.
Okay, so we're seeing the power of models in surprising places. But a lot of this boils down to understanding probability, understanding risk.
Right.
Most of us, we kind of think the future's unpredictable, just chance, right?
Seems that way often.
But Sumpter stresses this possibility of finding small edges hidden within probabilities.
And that's a subtle but really important difference. Individual events maybe seem random, impossible to call.
Yeah.
But look at lots of similar events together, and patterns can start showing up. Finding those patterns is how you find the edges.
He gives this great example. A startup CEO knows they've only got, say, a 1 in 10 shot of making it long term.
Right. Low odds.
But they're still pouring everything into this potentially billion-dollar idea. Seems kind of irrational on the surface, doesn't it?
You might think so, but then you look at it in terms of expected profit.
Expected profit, explain that.
Well, even if the chance of success is low, like 1 in 10, if the payoff is massive, like $1 billion,
Right.
then the expected value, which is just probability times payoff, can still be huge.
Oh, okay, so $10 billion times a 1/10 chance is still $1 billion expected profit.
Exactly. Suddenly that massive risk doesn't look quite so crazy. It's a calculated risk based on expected value.
And it's not just high-stakes business. He even brings it down to dating apps, like Tinder.
Yeah. Maybe a bit less glamorous.
But relatable. Like maybe don't expect the one on the first swipe.
Probably not.
But maybe rethink your whole approach if you're getting 0 results consistently. It's probabilistic thinking in everyday life.
Absolutely. It helps manage expectations, evaluate outcomes, even for stuff that feels as unpredictable as, romance.
Okay, now, to really get into understanding probabilities and how we, update our beliefs when we get new info, we need to talk about Bayes' theorem.
Bayes, yes. Crucial.
Sumpter uses this really vivid analogy. It's a bit scary, actually, being on a plane, and it suddenly starts shaking violently.
That gets your attention, doesn't it? Makes the abstract idea of Bayes' theorem feel very real, very quickly.
Yeah. You're on a plane, it's shaking, your mind immediately goes to, okay, what's the chance of a crash now? given this shaking.
Exactly. You're updating your belief based on new alarming evidence.
So we know the baseline chance of a plane crashing, right? It's tiny, like 1 in millions. That's our starting point, our prior probability.
Right, your initial belief.
Now, let's say the chance of a plane shaking badly if it's not crashing. P-shake, not crash. Maybe that's, I don't know, 1 in 100.
Okay. Possible, but not super common.
What we really want to figure out is P-shake. The probability of a crash given the shaking is happening.
And that is precisely what Bayes' theorem lets us calculate. It's a mathematical formula for updating that initial belief, the prior probability.
Using the new evidence, the shaking.
Yeah. It lets us figure out pure crash shake by using our initial estimate, the chance of shaking without a crash, and also the chance of shaking with a crash, which you'd assume is pretty high.
It's this really powerful way of taking what we thought was true, combining it with new info, and getting a more informed guess about what's actually going on.
Refining our understanding.
Sumpter then brings it down to earth a bit with this example of Amy deciding if her new classmate Rachel is unfriendly. He calls it her bitch model, so apologies for the language there.
Yeah, it's a very relatable way to see how Bayes works with our everyday subjective judgments, though.
How does that work?
Well, Amy starts with a prior probability, PM. Her initial guess at how likely it is a new person she meets will be unfriendly.
Okay, her starting assumption.
Then she gets some data. D. Rachel says something in the bathroom that sounds kind of mean.
Right. New evidence.
PDM is the probability she'd hear that comment if Rachel really is unfriendly, according to Amy's model.
Got it. And Bayes' rule helps Amy calculate PMD, the updated chance Rachel's unfriendly, given that comment.
Exactly. But it doesn't just consider Rachel being unfriendly. The denominator, the bottom part of the equation, is really important.
What was that?
Because it weighs up all the reasons for the data. Maybe Rachel is unfriendly, or maybe she's usually nice but just having a bad day, or Amy misheard, or,
Okay, so it forces a more balanced view.
Precisely. It stops you jumping to conclusions based on one little thing, which, as Sumpter notes, quoting Jane Austen, is generally good advice when judging people.
Be thoughtful, be considered, don't jump to conclusions. Good life advice, really.
And the story about Thomas Bayes' original essay, The Sunrise Problem, that gives us an even deeper look.
The sunrise problem.
Yeah. Bayes imagines someone new to the world trying to figure out the probability the sun will rise every day.
Okay, so they start with no idea, right? Could be 100% certain, could be 0%, could be anything in between, total uncertainty.
Exactly. A flat prior, we'd say. Any probability from 0 to 1 seems equally likely at first.
So how does Bayes help?
His brilliant insight was showing how observing sunrises one after another updates that uncertainty. After seeing, say, 100 sunrises in a row.
You get pretty confident it's going to rise tomorrow.
You get very confident. The probability that the true chance of sunrise is, say, greater than 99% goes way up. He calculates it as about 63.8% after 100 sunrises.
Still not 100% certain, though.
Nope. There's always that tiny, tiny chance, mathematically speaking, that the underlying probability isn't actually 1. You can get very close, but never absolute certainty just from observation.
Wow. That's a powerful reminder, isn't it? Even things that seem totally certain are based on probability. We should always be open to updating our beliefs.
Which leads us right into a really important point, the role of assumptions, and keeping an open mind when we use these models.
Right, because the math itself, the logic is objective, but the inputs,
like Amy's initial guess about how unfriendly people are,
those can be totally subjective.
Exactly. And Sumpter makes the point that Bayes' rule works fine with subjective probabilities, as long as you can, put a number on them.
So the process is logical, even if the starting point is personal.
Yeah. The key is how you update based on data following the logic of Bayes. It challenges that idea that math is purely objective truth. It's also a tool for reasoning about things, even subjective things.
And this brings us to needing to critically check our models. Be open to other explanations. Sumpter uses the example of claims by Dr. Christine Carter about screen time and teen depression.
That's a really good case study for the potential danger of just accepting a model without questioning it.
Because?
Well, Dr. Carter presented data that seemed to back up her view. But as, informed people, we should look at the model's validity. Consider other factors. Could something else be causing teen depression?
Like Sumpter says, look at all parts of the equation. He mentions he actually looked into the research, talked to his kids.
And concluded what?
That other stuff, like getting enough sleep, eating breakfast, seemed way more important for their well-being than screen time, specifically.
And that's crucial. Recognizing that considering alternatives, presenting all sides, that's not weakness, it's intellectual strength.
Right. It shows you've thought it through properly.
Thoroughness. Yeah.
Okay, so we're building this toolkit. Now, let's add confidence intervals and the normal curve. Sumpter uses roulette betting for this one.
The roulette example works really well for showing how randomness behaves over many, many tries.
Right. One spin. Totally random.
But do it 400 times. You start to see patterns, you can estimate the likely overall result and the range it'll probably fall into.
Okay, so for every £1 bet on red or black, the expected loss is about 2.7 pence.
Roughly, yeah, because of the green zero.
So over 400 spins, you'd expect to lose around £10.80.
On average, yes. But obviously, your actual result will vary. Could be better, could be worse.
And that's where variance and standard deviation come in.
Exactly. Variance measures how spread out the results are. Standard deviation is the square root of that, gets it back into pounds in this case. About a Reckner 109,996 per spin, he calculates.
And this leads to the confidence equation.
Yeah.
Which has that number, 1.96, in it. Where does that come from?
Ah, the 1.96. That comes from the normal curve, the bell curve shape we see everywhere. Heights, IQ scores, lots of natural phenomena.
Okay, the bell curve.
It basically describes how data tends to bunch around the average. So for the roulette spins, the outcomes after 400 spins will likely cluster around that expected £10.80 loss. Fewer results the further you get from that average.
And the 1.96.
In a perfect normal distribution, about 95% of the results fall within 1.96 standard deviations of the average, the mean.
Ah. So for roulette, we can be about 95% confident our actual winnings or losses after 400 spins will be within a certain range, calculated using that 1.96 and the standard deviation.
Precisely. It gives you a range of likely outcomes with a specific level of confidence around that expected loss of £10.80.
And this idea of confidence intervals wasn't new.
No, Abraham Demois first explored it, looking at coin tosses way back. He showed that after lots of flips, the number of heads would likely fall in a predictable range.
And then Laplace built on it.
Yeah.
With the central limit theorem, CLT.
Yes, the CLT. Hugely important concept.
What does it say again?
Basically, if you add up lots of independent random measurements,
Okay.
the total sum tends to follow a normal distribution, that bell curve again. It doesn't even matter what the original distribution of the individual measurements look like.
Wow. That seems powerful.
It is. The main things are that the measurements need to be independent and have a finite mean and standard deviation. But yeah, the CLT is a cornerstone of statistics. Lets us make predictions about sums of random things in loads of situations.
Okay, let's shift gears. Let's get into the influencer equation. Social networks. How influence spreads, who the key players are online.
Right, the influencer equation. Sumpter presents it as a mathematical way to see how connections in a network evolve. It uses something called a connectivity matrix, usually called A.
A matrix.
Yeah.
Like a grid of numbers.
Yeah. It basically shows the probability of moving from one person to another in the network.
Give me an example.
Okay, imagine a tiny social world. 5 people, Sumpter, maybe The Rock, Selena Gomez, and 2 less famous folks, Wang Feng and Li Wei.
Got it.
The matrix A would show the chance of, becoming each of those people tomorrow based on who follows who on Instagram today.
Becoming them. How does that work?
It's a way to model influence flow. You start with a probability vector, that's who you are today, multiply it by matrix A. That gives you A plus 1 who you're likely to be tomorrow, probabilistically. The equation is B plus 1, O equals A.
Okay. And if you keep doing that, multiplying by A over and over.
Eventually, you reach a stable state, a final vector, the stationary distribution.
And that tells you?
It tells you the long-term probability of ending up as each person in the network. And that probability, that's basically their influence score. People with high probability are the big influencers.
Ah. So that's how Google's PageRank worked and how Instagram finds popular accounts.
Fundamentally, yes. It lets them identify the most important nodes in the network just by looking at the connections. Doesn't need to know anything else about them.
Instagram apparently used this to find and promote popular accounts, which helped them grow massively.
Yeah, it's a powerful application. And the math behind it, from Andrei Markov, actually dates back way before the internet. Another case of old math finding new, powerful uses.
Sumpter also mentions that weird idea, the friendship paradox.
Oh yeah, that's a fun one. The idea that, on average, your friends probably have more friends than you do.
It sounds wrong. How can that be?
It's about how networks work. People with lots of connections are just more likely to be someone's when in the first place, right?
Uh-huh.
So if you pick one of your friends at random, they're statistically more likely to be one of those highly connected people. Christina Lerman found evidence for this on early Twitter data.
Huh. Weird, but makes sense when you put it like that.
Mm-hmm.
And while influencers are busy trying to, like, game the Instagram algorithm, A/B testing posts and all that,
Yeah, trying to figure out A.
Sumpter points out the real influencers are the programmers, the ones designing the algorithm Matrix A in the first place.
That's a crucial point. The unseen power of the code shaping what we see, who gets visibility.
Understanding this equation helps us see those filters.
Definitely. Sumpter even suggests trying to map out your own little connectivity matrix for your own network.
To see who's really influencing you, and maybe who you're missing.
Exactly. A little exercise in self-awareness about your own information bubble.
Okay, all right. Let's move to the reward equation. Decision-making. Sumpter uses Ed the bartender as an analogy here.
Right. Ed the bartender introduces the Markov assumption,
Which is?
a simplifying idea. The future state only depends on the present state, not the past.
So for Ed, how well he serves drinks in the next minute.
Depends only on how many people are waiting right now, not how busy it was an hour ago.
Got it. Focus on the present to guide action. Now, the reward equation itself.
That's about updating our internal estimate of how good a reward is based on what we actually get.
How does the equation look?
It's QT plus 1 equals QT plus UT. Your new estimate, QT plus 1, equals your old estimate, QT, plus a learning rate times the difference between the reward you got, or AT, and what you expected, which is implied by QT.
Okay, break that down with an example, like the Twitter retweet one.
Sure. Say you expect lots of retweets, high QT, but you only get a few, low art. Your internal estimate of the reward value of your tweets goes down.
And if a tweet you thought was meh suddenly goes viral, lots of retweets.
And then art is much higher than QT, and your internal Q value gets boosted. It's a constant feedback loop. Learning, adapting, expectations.
Does it actually work? Does it lead to the right estimate?
Amazingly, yes. Robbins and Monroe proved mathematically that this simple update rule over time will always converge towards the true average value of the reward. It's fundamental to how we learn.
This also connects to that explore-exploit dilemma, right?
Right.
Stick with what works or try new stuff.
Exactly. Sumpter uses ants foraging for food, leaving pheromone trails.
Ants, how does that relate?
Well, there's a parameter that controls how strongly they follow existing trails versus exploring new paths.
So strong reinforcement, low wow.
They stick rigidly to the best-known path. Might miss out on a newer, richer food source nearby. Exploit too much.
Weak reinforcement, high bow.
They wander around more randomly. Might find new stuff, but not efficiently capitalize on good finds. Explore too much.
Finding the right balance is key, and that's linked to tipping points.
Often, yes. A small initial advantage, slightly better reward, gets reinforced. Suddenly, everyone's following that trail or buying that product. Behavior tips.
Like fashion trends taking off.
Exactly. It applies way beyond ants. Understanding this reward equation, the explore-exploit balance, helps in our own lives, too.
When to stick with a job. You know, when to look for a new one. When to try a new restaurant. When to go to your favorite.
Pretty much. Sumpter's advice is basically, pay attention to now, track your rewards, notice if they're stable or changing.
And be willing to both explore and exploit, but be mindful of tipping points. Know when maybe it's time to pull back to stability.
It's about being more conscious about where you put your energy, acknowledging uncertainty, but still making choices.
Okay, now on to machine learning. The learning equation, gradient descent. Sumpter uses YouTube recommendations.
Right. YouTube's system is super complex, a neural network. But at its heart, it uses a learning equation to get better at predicting what you'll watch.
He simplifies it with the Shapiro-Peterson neuron example.
Yeah. The system predicts how long you'll watch a video. Call it U. It sees how long you actually watch. Then it calculates the error using a learning equation, like the squared difference.
And the goal is to make that error smaller over time.
Exactly. Minimize the error, make predictions more accurate. Gradient ascent is the math technique it uses to tweak its internal settings, the parameters, to do that.
Like climbing a hill in the dark.
That's the classic analogy. You take small steps in the steepest upward direction you can feel. That's the gradient. You ascend the hill of accuracy.
And Sumpter connects this to personal goals, like Noah trying to get more social media followers.
Yeah. The idea is, even if Noah's far from his big goal, if his follower count stops increasing much.
The gradient flattens out.
Right. That might mean he's hit a local peak. Continuing the same strategy won't help much. Time to maybe rethink the approach.
So focus on the progress, the gradient, not just the distance to the target.
That's a really valuable takeaway. And also learning to recognize when you've plateaued. Maybe be content with that peak instead of getting stuck trying the same thing over and over.
There's a catch, right? You can get stuck on a small hill, a suboptimal peak.
Absolutely. Gradient ascent isn't guaranteed to find the absolute best solution, the highest peak overall. Sometimes you need a bigger change, a different approach to jump to a better part of the landscape.
So it's iterative. Keep evaluating, experimenting, adapting.
That's the essence of learning and optimization, yeah.
Okay, let's dive into the financial world. The market equation. Sumpter uses it to try and model investor feeling or sentiment.
Yeah, the overall mood of the market. The equation looks something like dx HDT plus FXDT plus DW.
Whoa, okay. Break that down.
X is the investor sentiment. It changes based on three things. H is some underlying signal or fundamental value. FFX is a feedback loop, how current sentiment affects future sentiment. And ZW is random noise, unpredictable fluctuations.
And I had fun examples. Sony, Audio-Technica, Beats.
They illustrate different settings. Sony might have a steady positive signal, H. Audio-Technica, maybe more noise. Beats, strong positive feedback, FX, popularity breeding more popularity.
But these are simplified models, right, of something incredibly complex.
Hugely simplified. And Sumpter points out, even before the 2007 crash, some physicists were warning that these signal plus noise models just couldn't explain the huge crashes we see.
Like the dot-com bubble, the Asian crisis, they didn't predict those.
Not really, and that central limit theorem we talked about doesn't really apply neatly here.
Why not?
Because investor behavior isn't independent. People follow the herd, panic selling happens. Those actions are strongly linked, not independent random events.
So the math based on independence breaks down.
Pretty much. That comment about the Lehman Brothers crash being a 12 sigma event,
Yeah.
that just highlights how badly the standard models failed. A 12 sigma event should be practically impossible according to a normal distribution. Means the model was wrong about the risks.
Yet high-frequency trading firms like Virtu, they're incredibly successful.
They are exploiting tiny price differences millions of times a second, profitable almost every single day.
And Sumpter's contact, Mark, who works in HFT, he defends it.
Yeah, he argues it actually makes markets more efficient, narrows the gap between buy and sell prices, which lowers costs for big investors like pension funds.
It's definitely a complicated debate. The ethics, the impact on stability.
Mark's view, focusing on efficiency, that quantifiable outcome. Sumpter sees that as typical of the 10 mindset, data-driven, maybe a bit amoral, focused on logical consequences.
Right, nearly there. The advertising equation, correlations. Snapchat categorizing users, the example here.
Right. The advertising equation is basically just the formula for the correlation coefficient, measuring how strongly two things are related.
So Snapchat looks at user data. What interests tend to go together?
Exactly. They build these huge correlation matrices.
Yeah.
If people interested in Kylie Jenner also tend to be interested in makeup tutorials, that's a positive correlation.
And they use that to group users, like selfie-obsessed or makeup divas.
Pretty much. It allows much more targeted advertising. Show ads people are statistically more likely to care about. More clicks, more revenue.
But it raises that question about individuality again. Are we really that unique if our online habits fit into these neat boxes?
It definitely challenges that notion. Our digital footprints reveal patterns, similarities we might not even realize.
Sumpter really hammers home the difference between correlation and causation, though, using Cambridge Analytica.
Crucial distinction. Just because two things happen together doesn't mean one causes the other.
So Cambridge Analytica, targeting voters based on Facebook likes. That correlation didn't necessarily mean they could actually change votes effectively.
Exactly. It was a flawed assumption. Sumpter mentions research by Anja Lambrecht suggesting you need actual causal model stories about why advertising works, not just correlations.
Understanding the why is better than just seeing the what.
Much more valuable for effective advertising, yes.
And even with all the A/B testing Snapchat does, predicting people is still hard. We change.
Constantly. Interests shift, trends change. The algorithms are always playing catch up with complex human behavior.
Okay, last one. The universal equation, which isn't really one equation, more like logical thinking itself.
Yeah, it's the underpinning principles, the logic behind all the others. He uses the soccer bot example.
The bot that answers questions about players.
Right. Takes a natural language question, turns it into a database query, uses data to give a logical answer. That's algorithms in action based on rules and data.
And he contrasts this with, like, rigid rules, the 10 Commandments.
Yeah. The idea is the 10 equations aren't rigid rules like thou shalt not. They're guiding principles, frameworks for reasoning.
They empower you to draw conclusions from data using models.
Exactly. He also mentions Dijkstra's algorithm briefly.
For finding the shortest path.
Yeah. Super efficient, finds the shortest path to every point along the way, not just the end. A fundamental building block for so much tech.
And he touches on Poincaré, saying math theorems are just tautologies. A.
Mm-hmm. And A.J. Ayer saying they only seem surprising because our own reason is limited. Mathematical truths are seen as universal, true by logic, independent of observing the world.
So in this view, the Tin Society, the people using these equations,
Yeah.
they're guardians of intellectual honesty.
That's the idea, emphasizing. State your assumptions, use data rigorously, be clear about what you know and what you don't know.
Which is vital in a world full of, well, questionable information.
Absolutely essential for building reliable models and making good judgments.
Sumpter ends with a really important caveat, doesn't he? About the limits of pure logic, the need for intuition.
Yes. He mentions that Mike Tyson A.J. Ayer anecdote and the trolley problem.
Ah, the trolley problem. Sacrifice 1 to save 5.
It shows starkly how pure logic often fails us in complex moral situations. Our intuition, our empathy, considering feelings. Those are crucial too. Logic alone isn't enough for everything.
So, wow, we've covered a lot, this deep dive into the 10 equations.
Yeah.
It really is a powerful lens for seeing the world differently.
Absolutely. From sports betting to social influence, finance, ethics, the principles apply incredibly broadly.
And the big takeaways seem to be about critical thinking, right? Questioning assumptions, using data and models to refine how we understand things.
Definitely. Understanding financial markets, online networks, even just our own decisions. It's about being methodical, being aware.
And for everyone listening, these aren't just like abstract ideas. They're tools you can actually use.
Making better choices, understanding online influences, just being sharper about evaluating information day to day.
Which brings us maybe to a final thought for people to chew on.
Yeah.
Now that you've seen how these equations work, often behind the scenes,
Yeah.
what bit of nonsense in your own life, the chaotic stuff, might be worth looking at through this more data-driven analytical lens?
That's a great question. Thinking about the filters these equations revealed, which ones are you most aware of now, and how might that change how you see things or what you do next?